So on Monday, we left off about here, and we were looking at the lines of color that we can get by looking through those spectroscopes. And we said those lines correspond to differences in energy states. Okay, so we have two states, state A and state B. And we can think of these kind of like orbits, so orbit A and orbit B. And the energy difference between them is this H net. Okay. Then we did a practice calculation using the red laser pointer from earlier that we had already calculated the frequency of. Now, if you don't have the frequency and you have to find the energy, you can just use C equals lambda nu to find the frequency, just like we did on Monday to find the frequency here. But in this case, we know the frequency. So we're going to plug it into the equation E equals H nu. So remember, nu is that V thing, and that's the frequency. H is written on the board over here, 6.626 times 10 to the negative 34. So those were the numbers we plugged in, and we ended up with 3.0 times 10 to the negative 19. Very big number, very small number. Very small number. So each individual photon only delivers a very, very small amount of energy. But if you have a mole of these photons, so 6 times 10 to the 23, and you were to multiply those two, you're 10 to the 19, negative 19 and 10 to the 23. Well, the 10 to the 23 is going to kind of overwhelm it. You're going to end up with over 1,000 joules for just one mole of photons. Okay, so it can add up pretty quickly. All right, so for visible light, the energy tends to be 10 to the negative 19th. For ultraviolet, 10 to the negative 18th. So those are the kinds of numbers we would expect to see. All right, so just as review, if I wanted to find a wavelength, we didn't do wavelength, but we could from one of the equations we've already looked at. I can look on my microwave and find the frequency of 2.45 gigahertz. And I want to know what the wavelength is. Which of these equations includes wavelength? You can just shout out a letter. C. Okay. So C equals lambda. Lambda is light. And then nu is my frequency, which I have there. So let's try plugging this in. Okay, what we have to remember is that giga is times 10 to the 9th. So we're going to have, I don't think I have this spelled out on here. No, I don't. We're going to have C divided by nu. So we're going to have this divided by this, but it's going to be this times 10 to the negative 9th. Now this is going to give me a length in meters. I get 0.122. Anybody else get about that? Yeah. So about 122 millimeters, or about 12 centimeters. So some terminology, ground state and excited state. So in order to figure out where these orbitals are, we have to put the electrons in an excited state. But most of the time, we're thinking about the ground states. The ground state means all the electrons are in the lowest possible energy, lowest possible stationary states. And so when we draw these out, they're going to be lower down on the page. An excited state is when one or more of those electrons, instead of going to a lower level where it could be, is up high. We were imagining the atom kind of like the solar system with the nucleus like the sun, and the electrons on orbits around. So I've kind of drawn this. We call this the solar system model. Now we'll see later that this isn't actually what's happening, but it's good enough for what we're going to talk about right now. We don't want to have to draw out the atom every time we're looking at the electrons. And so what we're going to do is I'm going to have these circles move to the side, and we're going to just draw a line at the level where the top of the circle is. So where the top of this is, there'll be a line over here. Where the top of this is, there'll be a line over here. Okay? That's how we're going to get what's lower down and what's higher up. So lowest energy means closest to the nucleus. All right, so in our lowest energy, we can have just 2 electrons. It's a pretty small circle. The next one is further out, and it can fit 8 electrons. Then after that, it starts to get weird. So with my liberal arts students, I say, well, there's 8 in the next level, and that's where we're going to stop. But you guys get the complicated stuff. So right now, we're just going to think about those 8, but we'll get to the other 10 before the end of class today. So there's 8, and then in another portion, there's 10. Right now, we'll look at 2, 8, 8. So if we look at the elements on the periodic table, we have 2 in the first row, 8 in the second row, and 8 in the third row. And there is a connection that we're going to see coming here. Okay, the lowest energy level is this one. And so if I only have 2 electrons, they're going to go down there. Okay, if I have 13 electrons, I'm going to fill up this, then I'm going to fill up this, and the leftover ones will go in the very top. Okay, so we have different kinds of electrons. The ones that are closest to the nucleus, they're really strongly attracted, so it's hard to pull them away. And the ones that are farthest from the nucleus are less attracted, and it's easier for them to interact with other atoms. So the ones that are farthest away, we call valence electrons. So they're in the outermost energy level or circle that has electrons. Now, there might be other circles out there that don't have electrons, but the outermost electrons are called valence electrons. Those are the ones that can actually do chemistry. So they can be shared with other atoms. If there's very few of them, they might be pulled off. If they just have like one missing spot, they might like yank an electron from another atom just so they can fill it up. Okay. So these are shared in a covalent bond or gained or lost to form ions. And then next semester, we'll talk about the octet rule. The atoms tend to be the most stable when this valence shell is full. So everything besides that outermost ring is called core electrons, whether it's just the 2 on the inside or if there's several layers. If it's not the outermost ring, it's called a core electron. And those electrons, unless we're doing something extreme, don't go in. So we say they are inert. They are not chemically reactive. But for the most part, if I'm just mixing things in a beaker or a test tube, those electrons are staying put, not doing anything interesting. So it's going to be useful for us to figure out which electrons are in the core and which electrons are on the outside, and most importantly, how many are on the outside. Okay, so where we're going with this is we're going to be doing electron configurations. They're going to help us to see where are all the electrons that are in an atom or an ion. So we're going to start with neutral atoms, but we know, of course, some things just always form ions. Okay, and that's going to tell us about how those materials might react. Okay, so back to our circle here. If I'm looking at hydrogen, hydrogen's element 1, it has 1 proton and it has 1 electron. So that electron in its ground state is going to go all the way to the bottom, right? If I have helium, so let's remember that hydrogen just has 1. So we're going to come back to that. If we have helium, it has 2 electrons. Okay. Have I filled up my bottom level yet? No, because I can fit 2 electrons there. So now it's full. Okay, so hydrogen with just 1 is over on this side. Helium with 2 is over here, but its level is full. So now if we go to lithium, element 3, I have to put an electron in the next level. How many valence electrons does it have? Just 1. Just like hydrogen, they both have 1 valence electron right underneath each other on the periodic table. Now, when I go to beryllium, beryllium has 2. Okay, just like helium did. But helium was full. Beryllium is in a layer that wants 8. Okay, so it's not full yet. And so we have a new column that starts with beryllium. Okay, now I'm going to fast forward. So if we think about neon, neon would have 10 electrons, right? And 10 electrons would account for 2 plus 8. So that would completely fill that out. Okay. Neon is also right underneath helium. My next element would be sodium, which is 11. So we'd fill in those first 10, and then we would have 1 on the outside. 1 valence electron right underneath lithium with 1 valence electron right underneath hydrogen with 1 electron. Okay. So you can see that we're starting to build the periodic table based on valence electrons. If we go to our next one, magnesium has 12 electrons. We're sticking one more in. It's not full, so it doesn't go all the way over where helium is. It's right underneath beryllium. Okay, so the construction of the periodic table is based on the number of valence electrons. Now, did Mendeleev know that when he put it together? No. What he knew was that they have similar properties. But the reason they have similar properties is because they have similar numbers of valence electrons. These all form a +1 charge because how many valence electrons does group 1 have? 1. Group 2 has 2 valence electrons. What's its common charge? 2. Okay, so there's a connection there. Remember that you don't need to write this part down. This is just kind of a heads up. I'm telling you some stuff. We're making some assumptions. It's not all exactly true. The Bohr model is based on the idea of the hydrogen atom. So if you take P-Chem, this is what's called the hydrogen atom quantum model. And it works really great if you only have 1 electron, like for hydrogen. It doesn't work well for polyatomic ions. We'll talk about some of the differences in just a minute. So P-chemists, the people who study this kind of thing, count this way. They count 1, 2, many. When I have one object that I have to account for its motions, pretty easy to do. When I have 2 objects that I have to account for, the math gets a little complicated, but I can do that. If I have 3, it gets really complicated. So there's that TV show, the 3-body problem, or 3-body, something like that. The 3-body problem is that when I have 3 things I'm trying to account for their motion, it gets really, really complicated, and the math is just too hard for us to sort out. Okay? So that's where that problem comes from. In a hydrogen atom, I have the attraction between hydrogen and the nucleus. That's one interaction. Once I throw in an extra electron, the electrons are both attracted to the nucleus, but they're repelling each other. So I have to account for the interactions between all 3 of those things, which I can kind of do. But once I get to lithium and there's 3 electrons involved, then it gets super crazy. It's just really hard to do. Okay. So other than to know that there's a little asterisk by what we're saying here when we say this is, what's true, we're approximating it based on what we know for hydrogen. Okay. You don't really have to know the details of this. We talked about that. Talk about this. Oh, we didn't talk about this. Okay. So here is Bohr's model with our rings going around. And we were connecting this to light. Light can do 2 things. Light can come in and light can go out. So when I see something that has color, that light is being absorbed in. Okay. So absorption looks like this. A light goes in. Oops, I did that one in the wrong direction. And the electron moves away. Okay. Now, this is no longer in the ground state. The electron's not where it wants to be. So it's going to eventually move back down. When we see color, that tends to happen through some relaxation of vibrations and things like that. It doesn't give off light. But if I have it go automatically back down, then we have emission. Light is emitted, and the electron goes back to its ground state. Okay, so 2 things. Absorption is light goes in and the electron goes out. Emission is light comes out and the electrons go in. So right at the end of class on Monday, we were looking at the hydrogen lamp, and we could see like 4 colors, like a red, kind of a greenish color, a blue, and maybe a purple. Okay, so where does that come from? If there is an electron that through all the electricity that's being pumped through there, it gets blown way out from the nucleus and it's trying to find its way back down. In hydrogen, it's going to let off ultraviolet light because the difference in energy between this first and second level is huge. It's in the ultraviolet range. And the difference in energy between these 2 is much smaller. It's in the visible range. And then they get closer and closer together. So by the time we're between 10 and 11, it's like a difference in temperature can make a difference between. So if we are falling down to energy level 1, the electron moving in, emission is going to be in the ultraviolet. but we can't see ultraviolet. What we were able to see was visible. So what we could see was the electrons that were falling down to energy level 2. Okay, so if it goes from level 3 to 2, we see the red light. Now, of all the colors we saw, red, green, blue, and violet, which one's high energy? Which one's low energy? That's lower energy, okay? So it's the closest two orbitals here that are giving us the red light because that's the lowest energy. So our next highest energy is going to go from level 4 to level 2. Our next highest energy of those colors is going to be the green. And then the next level out is going to be the blue, okay? And then further out would be the purple. And then there's another purple that usually we can't see in those spectroscopes because they don't go wide. Okay, so depending on which energy level it's coming from, we get a different color. And using those differences in energy, we can figure out how far apart each of them is. Okay, so this is a diagram from your book. It kind of summarizes everything. It's all crazy here. Let's look at what it's saying. So over here, we have absorption. Now, it turns out that the more protons I have, the more those inner rings get pulled into the nucleus. And so the rings spread out. The ones very close are pulled in really, really tight. And there's more of an energy gap between the ones as you go out. So for hydrogen and helium, that first gap is in the ultraviolet. But by the time I get to sodium, if something is moving down to energy level 1, say 2 to 1, that's going to be in the X-rays, okay? And then by the time I get down to, say, tungsten or lead, one of our heavier elements, even going from 3 to 2, the second energy level difference would also be in the X-rays. So that's one difference. They're not all visible in the 2 to 3 range. We talked about these levels. Now let's get more into the complexities. We don't really have like one long shelf to put all these electrons on. It's really sets of orbitals, and the orbitals are going to be segments of these lines. So in the same place, we're going to have segments. Now the orbitals can each hold 2 electrons. So this is just one orbital down here that had 2 electrons. So to hold 8 electrons, I need 4 orbitals. Okay. In the hydrogen atom, they're all at exactly the same energy level. One of the complexities that is introduced when I have more than one electron is that they differ slightly. What we find is one of them is a little bit lower and the other 3 are the same energy level. The next level, having 8, is also going to have 4 electrons, or 4 orbitals rather. Each of those orbitals can hold 2 electrons, but we don't use circles to represent them. We use arrows. So it looks like this. So we're going to start drawing diagrams that have these arrows. And what the arrows come from is just like the Earth can spin on its axis, electrons can too. They can spin clockwise or they can spin counterclockwise. Okay, so this is just showing us, is it spinning clockwise or counterclockwise? And one of the rules we're going to see is that in a given orbital, like this one here, you can only have 1 electron spinning clockwise and 1 spinning counterclockwise. You can't have them both doing the same thing. Okay, they have to go in opposite directions. Okay, so that's why we should use the arrows to make sure that we have things pointing in opposite directions. All right, then we have those other electrons that I said for liberal arts, we don't even talk about them. We're going to talk about them with you guys. So we have another set that is also in energy level 3 that exists in here. Now, this set, we only had 1. This set is a set of 3. So there's 1 and then 3. And the other ones, they're going to be 5 orbitals. So 1, 3, 5. Okay. So key things here, each orbital, and these line segments represent an orbital, can hold 2 electrons, and we use the arrows to represent the electrons. So an arrow is an electron, a line segment is an orbital. We got lots of orbitals here, and we want to be able to distinguish one orbital from another. So our next slide is going to be, how do we talk about these? So we distinguish them by their shape. Okay, so the shape just means the area where we can find the electron. Okay? So you might think of the electron like a car and the orbital like the road it can travel on. Okay? So where all the road goes defines the shape of the orbit. Okay, so if I had New Circle Road was my my road that I could travel on, it would be a circle. Okay. Now they don't actually move in circles; they move in 3 dimensions. So it can be on the inside of this and all the way on the outside. So it kind of has like this whole big field it can drive around. Free range electrons. They actually spend most of their time closer to the nucleus. Okay, so the first kind of orbital is a sphere. We call this an s orbital. And this is kind of how we think of atoms looking. So most people kind of think of orbitals as looking like this. Every energy level, every layer, 1, 2, 3, 4 on out, is going to have one of these guys. Okay, so there's one in each layer. So that second layer that had 4 line segments, one of those line segments is representing a sphere like this. And the other 3 are representing a different kind of orbital. That kind of orbital is a p orbital. So it's kind of in shaped like an 8 or an infinity, but remember it's 3-dimensional. Now this orbital can have direction. So a sphere, it's pretty much the same in every direction. But we might say this one is pointed up and down, right? Well, I can also have the same orbital pointed side to side. Okay, and we distinguish between these by the axes that it's on. So we usually call the up and down axes the z-axis and the side to side the x-axis. We don't always, so sometimes you find them in different directions, and physicists like to do things different from chemists, so you just kind of got to double check your axes. The one that's kind of hard to see is the one that points in and out. Okay, so if we think of it looking like this, that would be really hard to draw head on. You wouldn't be able to see the back of it, okay? But on your paper, the one that is closest to the sphere, that is trying to represent the one that's coming in and out of the page. And we said the next set, there are 5 of them. We call those the d orbitals. They have kind of a 4-leaf clover shape. And just like the p orbital, they can have a direction. So this one is kind of, facing you full front, but it could like turn on its side, or it might lie flat. Okay, but because it points outward instead of along one axis, we use 2 letters for it. So if you look on the diagram here, we will have this one that looks like a clover here. In the corner, it says DYZ. Okay, so the z-axis is up and down, and we can see it's going up and down. And the y on this one is going side to side. And so that's why it's called DYZ. In that picture, the X is coming out at you. Okay. And then if it lays flat, then it doesn't have any Z component. And so we call that the DXY. Okay, so we can label the orbitals based on which axis it's pointing on. The reason I point that out is there is, I think, 1 or 2 questions on active that asks you about which kind of orbital it is. So you're going to have to look at the axis and see how to label it. Okay, so you'll notice that there are 4 of those. I told you there are 5 d orbitals. So 4 of them look like clovers. One of them's kind of funky looking. Looks like this. Okay, so I say it has a ring of Saturn or a donut around its middle. So somebody in the last class said, well, where do these shapes come from? How do we know these shapes? How do we get these shapes? And the short answer is math. So if you've had enough math, you've been introduced to imaginary numbers. And the wave functions that are where these shapes come from involve imaginary numbers. And these are the probabilities of those wave functions. And so it involves turning something that is in imaginary space into real space, which I haven't done since I was in college, and that has been a really long time. So that is all the explanation you're getting from me. Feel free to talk to Dr. Dickinson or Professor Granlund, and they can give you more details. We're going to talk a little bit about the quantum numbers are used to describe the orbitals. Remember, each orbital is a home for 2 electrons. Each energy level, starting at the bottom, has a number. It's called the principal quantum number, and we use the letter N for it. Okay, so the bottom level is 1. The next level is 2. The next level is 3. Principal quantum number, energy level. In our first energy level, there is only 1 orbital, and so there are only 2 electrons. In our second energy level, where n equals 2, there are 4 orbitals. One of them is an s, and 3 of them are p's. So altogether, we can have 8 electrons. So normally when we talk about orbitals, we use these 2 things to describe. We say what energy level and the letter for the kind of orbital. So it's a 1s orbital or a 2p orbital. But so the energies have those sublevels. The sublevels refer to, is it in the s level or the p level? So we're going to change analogies now. Now, instead of the electron being a car, it's going to be a person living in an apartment building. And the atom is that apartment building. Okay? On the first floor of the apartment building lives the super and his wife. And that's it. Everybody else has to go up to level 2 or beyond. But on level 2, there's the apartment that's right above the super. And then if you turn the corner into a different hallway, there's just like a little step up. You have to go up 1 little step. And then you can go to the P hallway. Okay, so it's like a different hallway, and it's a slightly different energy level, but you're basically the same floor, right? When you get to the 3rd level, then you can turn the corner again, and there's another step up to the 3rd level where the d electrons are. Okay, so we have 2 ways of describing these. We use the quantum number n, which is the principal quantum number, to tell the energy level. And then even though they're letters, the quantum number here is called the angular momentum. And each of those letters corresponds to a number. I think we use letters because otherwise there'd just be so many numbers it would just get really, really confusing. Okay. So here's the apartment building. Every floor has an S. Only floors 2 and above have a P. Only floors 3 and above have a D. In hydrogen, we only have 1 electron. That's where the super is. All right. Each of these corresponds to what we call a wave function. So there's a mathematical function that involves sines and cosines and all things we're not going to really think about. But you could graph that. So you could put on axes what those different equations are. So the equation for an s orbital might look something like this. Then you square it to find the probability. So this represents the probability. And you can see the probability of finding the electron isn't at the edge. It's in the middle. The electron spends most of its time in the middle. Very little of its time on the outside. Okay? So what we are showing with that shape is we're saying 95% of the time, this is where the electron is. There's a teeny tiny percent of the time that it might be outside of that space, but most of the time it's going to be in that space. Okay. And that's how we get those shapes. All right. So we have the orbitals. Each holds 2 electrons. N is going to be the principal quantum number. L is what we use for the angular momentum. So the orbitals with the same L are in the same subshell, which is the same hallway. Okay. So L is kind of the overall classification for S, P, and D. So I say, what is L? You're going to give me a letter. All right. And then we've talked about how we can use the axes to describe. So this is YZ, or that's the PZ up there. This is the DYZ. These also correspond to numbers. And those numbers are magnetic. So we use an M to distinguish that. And that tells us which of those short lines we're on. Okay. So there are 3 short lines that correspond to P. And that corresponds to one that's up and down, one that's side to side, and one that's in and out. And each of those has a label. And that label could either be X, Y, or Z, or we could use the M numbers. We'll talk about what those M numbers are on Friday. So is this enough for your brain for today?